gives you the instrument connection view. This is the instrument. If it's got the green halo here, it means it's ready to connect. So we hit connect. And we have Trio software. Okay, so first thing I'm going to go over are the calibrations you guys need to do. And the first calibration is under the calibration ribbon here, is the instrument calibration, instrument inertia calibration. So because this is a CNT rheometer, everything's up here, you need to correct for inertia. Okay? Very easy. If we go to the help button here, everything you need to know about trios and the instrument is under the help button. If we go to calibration and do a search, it's got all the calibrations you can do with this instrument. A lot of these are accessories, the temperature calibration, instrument calibrations, right? And this is where it talks about the instrument inertia calibration. So anything you can do with the software or the instrument is in the help. But calibration, instrument inertia calibration, I think under that help file it says it needs to be done at least once every 3 months. I typically tell you guys to do it once a month, or if you use the instrument only, once every couple weeks, you might as well run it. It's very easy to do. You come here and you hit calibrate. It gives you a status bar and it takes 30 seconds. Okay? It gives you last calibration date, time, and the value you had. And if you do this calibration, it should be very close to the last number. It's going to be a little different, but so last one was 20.2. This one's 21. So 21's around normal.
What's the acceptable deviation?
If it goes over 22, there may be an issue with the bearing. And you just hit accept. All the other calibrations are geometry specific, so let's tap the geometry so I can show you those. Look for the So we have a 40 millimeter 2-degree cone. And if we go to experiments here on the file manager side, and we go under experiment and geometry, right now we have the smart swap for the geometry toggled. Okay, so it will read this barcode. So all the geometries have barcodes on them. If we install this and give it a second, it should read it and it should change this geometry to the 40 millimeter 2-degree cone. And there it is. So it read the geometry and it changed it to the 40 millimeter 2-degree cone. So now this, whatever geometry is right here is the active geometry. Okay? So now if we go over here to geometries, select the 40 millimeter 2-degree cone, it comes up with the geometry setting, so 40 millimeter diameter, it has the cone angle, all that stuff. And if we go down here, there's a tab here that says calibrations. And these are the other calibrations you're going to be concerned about, okay? And the first one here is the geometry inertia calibration. And it's basically doing the same thing, and it gives you instructions too. It says, please ensure that a geometry is attached and the spindle is free to rotate. Okay, the geometry is attached, and we hit calibrate. So another 30-second calibration. It's doing the same thing as the instrument inertia calibration. It's just going to get a number for the geometry, and it's going to combine those.
And this inertia calibration would be the same for all geometries as well?
Yeah. Well, each geometry has its own calibration, so, right, but these are all the same.
And then, sorry, one other question. On that workspace on the left, those are all the geometries that you have installed?
Yeah.
Earlier.
Those are all your geometries. Yeah. They're all installed and ready to go. The second calibration here is the friction calibration. Again, it takes 30 seconds. Typically, it's from 0.27 to 0.3 as a value. Hit calibrate. And what it's going to do, it's going to spin the geometry and correct for any friction.
So each time we use those geometries, we have to do...
No. It's more of like the instrument inertia once every couple months or once a month. Again, if you only use the instrument once every couple weeks or it's been a while, you might as well run that because it's a good way to make sure it's working. Because if these numbers are close to what they were before, they're not going to be exactly the same. This instrument's working, right? The only other variables would be the gap and temperature that could throw you off. Okay? The next calibration here is the gap temperature compensation calibration. So I do not run this calibration. It's because it can take a long time, and if I did it for every geometry, I might be here all week. So you guys can run it. And basically what this calibration does is it compensates for heat expansion, right? So when you're heating this up and this up, what's going to happen? They're going to expand, right? So, and when they expand, your gap changes, right? So your gap is one of the variables for rheology. It's a very important variable. So, and what this does, this calibration, is it will correct for that. You only need to run this calibration if you're doing temperature ramps. If you're just doing isothermal runs, you would just go to that temperature and zero the gap. You don't have to worry about thermal expansion, right? So only if you're doing temperature ramps. I assume the people that are going to be using the oven will probably be doing temperature ramps. It's very easy to do. It just takes a long time. All you do is you put your start temperature in. So this calibration only needs to be done once, right? Because the factor for heat expansion isn't going to change for the geometry, so you don't have to run it just one time. And you would put the range of all the procedures you're going to run. So whatever you think your range is going to be for everything you're going to run, right? So if we were running on the Peltier plate, you start at 0 to 200 if you wanted to, right? And then you would just put in the ramp rate, which is typically for rheology, like 3 degrees per minute is a good number. That'll give you a range of like from 1 to 5. And then hit calibrate. And what it's going to do, probably what would want to bring this down a little bit. What it's going to do is it's going to bring the bearing assembly down, and and it's going to have the geometry hit the bottom plate, and it's going to put like 4 newtons of axial force on the geometry, and then it's going to start heating up at 3 degrees per minute. Once it starts expanding, it's going to just try and keep it at 4 newtons, right? And it's going to do that by moving this assembly up and down. So it'll go all the way up till the end temperature, and once it stops, it'll give you a factor, and you just accept it. So it's very easy to do. It just takes, you know, if you're doing a big range, it's going to take a long time, right? So this would be something you could start, leave, and then come back. And what will happen, it will have a factor, and it'll say accept. Okay? Now, we don't do it with a cone, right? So one thing about cones, the gap, the sample gap for a cone is very small, typically 50 microns. So you normally don't run temperature ramps with a cone. You would use a plate. It's hard to control the gap with such a small gap in the heat expansion with a cone. So typically you'll do temperature ramps with a plate. So you don't need to worry about doing that calibration with the cone. And then the last calibration here is rotational mapping. So what rotational mapping is, it's going to map the coder, the thing on top, is what it's mapping. And basically, it's mapping out those small little torque variations that I was telling you about earlier. Right? Every bearing has tiny little microscopic imperfections that cause torque variations, and that's what it's mapping out. Okay? There are 3 different levels of mapping. There's fast, standard, and precision. Mapping, a lot of it is determined by your sample. If you're running really low viscosity fluid, water, whatever, at low torque, you're definitely going to need the map. You may need to run a map after every sample. Okay? And if you were doing that, you would do a precision map with 2 iterations. That's the most mapping you can do. Anything over that is, if you did like 10 iterations, it does it. It's not going to do anything. So precision, 2 iterations. And that can take up to 10 minutes to do. So if you guys were doing low viscosity fluids, like I said, like water, it could be something you may have to do every time you run a sample. But we're going to run some S600 oil, which is 1000 CP oil, and a standard map with 1 iteration is fine for it. Okay?
For oil?
Yeah. So I'm going to do a standard map, 1 iteration. It's going to take 3 minutes. I'm going to hit calibrate. This message just says the gap is currently unreferenced. The geometry must be free to rotate to run the mapping. Is it free to rotate? Yes. So again, mapping is something, if your samples are gels or something a little more viscous, then maybe just mapping in the morning when you come in is fine, right? So it's just determined a lot on your sample. If it's a really low viscosity sample, what you'll see, and you run it at low torque, if you don't map it, you may see some noise, a little bouncing around, right? Because you got to figure the geometry is just hanging there, and it doesn't have a lot of torque on it, and no resistance from the sample, right? If it's like water, so it's just going to be And that's what mapping helps with.
So for gels, usually take 2 iteration.
What's that?
For gel, usually take 2
No.
iteration.
Like if you're running a gel, a standard map with 1 iteration is.
But the liquid will take 2.
Yeah, if you're running like, something that's really viscous, if it's, like 10 CP or something, you would probably need to do a precision map with 2 iterations. A big industry for this instrument is the asphalt industry, right? So they test the viscosity of asphalt and they can determine the quality, right? Just by running viscosity tests. It's so sticky and nasty and they don't even really need to do a map. Doesn't matter, but I would still suggest if your samples are more viscous like that, at least run it in the morning before you're running your tests.
Is there an attachment to actually determine the viscosity of the sample?
Is there an?
Attachment to actually determine the viscosity?
Yeah,
of
we're
the
gonna
sample?
run some right now.
Perfect.
Okay, so mapping, it doesn't give you a value, it just gives you date and time it was last mapped. If there was an issue with the mapping, you'd get the little yellow exclamation point, but if you get the green check, you're good to go, okay? So, those are the calibrations you have to do for this sensor. Very simple, not difficult. Okay. So now if we go over to the right here, we have our control panel, and these are all the manual controls for the instrument. We have gap, environmental, which is whatever environmental system you're using, which for you guys would be Peltier plate or the oven. And then manual motor controls, okay? So we've got the airline instrument on, we've installed the geometry, we did the calibrations. There's one last thing we need to do before we can use this instrument. And that is zero the gap, because the instrument doesn't know what the gap is. And zeroing the gap, you want, if you're running an isothermal test, you want to zero the gap at the temperature you're running the test at, right? So, because if you came in and zeroed the gap at the room temperature now, or what it is, I think because I got this set to 20, so that's reading 20. We zeroed it now, but our test was at 40 C. There's going to be some expansion. Your gap's going to be off, right? And your gap is one of the variables for your data. So we're going to run some S600 oil at 25 C. So I'm on the environmental ribbon here. I'm just going to put 25 C in there, and I'm going to hit apply. And it came up to set temperature, and it's going to go quickly to 25 C. That stabilize a little bit. Any questions? Anywhere there's a little green box, that is an options box. And basically that just means you can go in there and change settings for that function. Okay, so if we go in here, we can do a span and offset calibration, or So that's got the waiting for temperature values, right? So if you set waiting for temperature in a procedure, it's going to wait 0.2 C in time, okay? If we go to our gap controls, over here we have stop the head, so for moving up and down. Go to geometry gap. So the geometry gap for a cone is the truncation gap, which is 52 microns. So for a cone, you have to run it at the truncation gap, okay? I'll go over the plate when we run another sample. So if we hit this guy here, it's going to go to 52 microns. We have trim gap, which I will go over trim gap when we run the other sample. Raise the loading gap. So the loading gap is right here, 42 millimeters, or 45 I mean. That's the gap you're going to load your sample in. Okay? So you can change that. If you find it's not high enough, you can change it to whatever. This is an important one, zero gap. That's what we're going to do. Zero the axial force, so how much force is on the sample. You can tear the gap, so you can do a manual gap if you wanted to. And then we have up and down. Okay? If you were lowering this and it hit the bottom plate, there is a safety, it will stop. Once it gets to 50 newtons, it will stop. So just keep that in mind, but I don't recommend doing that a lot. And again, we have an options here box, and there are a lot of different options under the gap. So like gap zero mode, you can zero it using axial force. The closure rate, it can be linear. So right now in standard mode, I find it works well. It's basically to zero, it's gonna bring the top plate down on the bottom plate, and again, put like 4 newtons on it, and it's gonna figure out the zero. The closure rate, once it gets pretty close to the bottom plate, it's gonna slow down. But you may have samples, you don't want it to squeeze the sample out, so you may want to go really slow. So that would be a function you could change. Okay, so we're at 25C. We can zero it. We go to zero gap, and it's going to turn the geometry. Watch, it'll probably put like 4 newtons of axial force on there, or up here. And it's done. Head zero completed. Do you want to raise the head to loading gap? Yes.
And then all that can just be done with the buttons. So,
And then what?
this can all be done as well with the button.
Yep, you can do it.
Gap.
Yep. You can do it up here with the gap control. Okay, so what, I use down here. So, if we look at the geometry settings, so with a 40 millimeter 2-degree cone with a 52 truncation gap, 52 micron truncation gap, with those settings, this gives you a minimum sample volume right here. So 0.58 mil, 0.6 mil, okay? Which is important. for rheology. You want to make sure you got at least 0.6 mil there, okay? I am just going to pour some on the plate because I got a pretty good eye, so. Okay, so now I can go to geometry gap, and it should go to 52 microns. Okay, so we're at 52. So I have extra sample on here. What do I need to do?
What?
Wipe it.
What's that?
Wipe it off.
I need to trim it because if you have too much sample around the edge of the geometry, your viscosity will be high, right? So what I like to do when I'm running a test like this with a fluid, I like to go to the motor control, which under motor control you can do lock, you can lock it, zero displacement, you can do a manual oscillation, you can go to a home position, and then you can move to alignment position for other types of geometries you don't have. But we can also set a shear rate. So I like to get the geometry turning a little bit, especially for a fluid, in case there's any bubbles or anything, try and work them out. But if I select signals, because you can add more stuff here, I'm going to do viscosity. Show signals. Oh. Alright, well, I'll fix that. But if we look now at viscosity, it's giving us the actual viscosity now. 1.21. At 25C with this oil should be 1.074. So it's high because we have too much oil.
And then, sorry, one question. For that shear rate, do you normally default to just 40?
Yeah, because I'm going to do a ramp, and 40 is like right in the middle of where I'm ramping up at. I'm going to hit 0 on that, and then hit apply. So I'm going to trim the excess. And I'm going to hit the lock so the geometry doesn't turn while I'm trimming it. Right? And all I'm going to do, I stay in a lot of hotels, I got a old hotel key, because you don't want to use metal on this surface, because it will scratch on the Peltier plate. So you want to use either plastic or wood, okay? And we're just going to trim off the excess. And it helps if we use the LED.
So the bubbles inside will also influence the
They can, yeah. Yep. Okay, so now we can set up a procedure. So the first ribbon here is sample information. So if we do as left cannon S600 oil flow test installation 03 11 2021. Oops. Operator. Yes, so the project notes. So this is the actual file name right here. If we go down to file name, this is the default file path, C drive program data, TA instruments, trios data. If you go to this little box, you can have it go wherever you want. I set up a service folder with installation. Okay, but you can have it go wherever you want there. Need to make sure we have the correct geometry. Because if you have a 40 plate and you have the cone loaded, your data is going to be way wrong.
So when should we use a cone?
A cone, I'm going to run a test with a cone, but a cone, you typically you use a cone for, so you'll use a cone for fluids and lower viscosity, oils, fluids. You can use a plate with those samples. The issue with a plate is you'll get edge effects, right? With a cone, you don't. The problem with using a cone, if you have particle sizes, I think 10% in your sample of the gap, the 52 micron gap, you can't really use a cone. So if you have large particle size, you would need to use a plate.
Okay.
Right? Cones are good for fluids. Okay, so if we go to procedure, this is the actual procedure we're going to run. Anywhere there's a drop down, you can select the test. So you have a choice of oscillation, flow, step. We're going to do a flow test, but and we'll run an oscillation too, but I'll go over these other guys real quick. Step would be a test like creep or stress relaxation or stress growth. These are types of tests where you're putting torque on a sample and then you're just seeing what it does. So there's no oscillate, you just put some torque on and you just want to see how the sample reacts. Those are those types of tests, okay? Other tests. These are different accessories, but axial tests would be a different geometry too. Axial test is like a mini instron, right? If you had the correct geometries, you could have it where it just pulls the sample. You don't have the correct geometry for that. So. Conditioning, this is where you would do like pre-test sample conditioning, like set a temperature, start a pre-shear, right? Because if you're running fluid, when you just start the test, you'll see viscosity will be high and then it'll drop down because it's just starting. So if you had to do a pre-shear and then start the test, it'll be right nice and smooth. So sample stuff. You can also, under conditioning, have axial control. So if you had samples that expand or contract, it doesn't sound like you guys will be running stuff like that. But if you did, you can control the axial force of the instrument. So a lot of like people that are like carbon fiber composites, they'll use axial control because their samples cure and they also contract or expand a lot. And basically what this does, well, we can't do it because it's a cone. You can't run it with a cone, it's got to be a plate. But what it does, it will control the axial. You may just say, just keep the axial force at 0, right? Or you can put some force on it. And what it does is once the sample starts to expand or contract, it will, instrument says, oh, I need to keep this at 0. So it'll move the gap up and down to do that. So only for samples that expand or contract. Or if you were doing like torsion, a different type of geometry, you would maybe put some tension on a sample. And then sample loading would be temperature stuff, or target gaps, or closure profile. And then you have end of the test stuff, like once the test is over, set a temperature back to where you want to go. Okay, but we're going to run a flow test. And then under flow test, you've got some choices here. Peak hold, which is basically just going to go to a one shear rate and just sit there, right? Or ramp, it's going to ramp up from a low shear rate to a high shear rate. Ramp loop is going to go up from low to high and then back down. And then temperature ramp, which again, you can typically, you would do that with a plate. Right? We're just going to do a ramp at 25C. It's been sitting there for a while, so we don't need a soak time. And we're going to run it for 240 seconds. And we're going to, okay, so this latest version of Trios has 2 modes, express or unlimited. So express is just basic tests where you can't change any of these functions and they don't have some functionality that unlimited does. Okay? So we have more functions with unlimited. So I'm going to run stress over shear rate and then sample how much data we're taking. So let's see, 10 seconds a point. And that's good. You can add steps here. And you can delete all steps here. You can save your procedure right here. You can open save procedures here. And then you can open a procedure template.
What is the soak time? Is it
Soak time is so how much time it's going to sit there at temperature. So 180 seconds before it starts the test, it'll sit it for 180 seconds. And then here we can delete these guys. Okay? So let me get started. See what happens. When you hit start, you got running time here, and it goes to the results file. It goes to results file. Everything's right click, scaling, properties. You can set up the graph if you wanted grids and all that stuff. Right? all your axes. You want to change stuff there, you save it up here.
So this thing at the bottom controls both the like the plate temperature as well as the oven temperature.
As well as the, no.
No.
No, it only circulates fluid through the Peltier plate.
Okay.
Okay, so the Peltier plate heats and cools electrically, right? So we need fluid running through it because it will overheat if you were going up to higher temperatures. And it will, the fluid will help you get down to lower temperatures. The oven just has air going through it.
Okay.
So 20 seconds left. Okay, so it went to idle. That means it's done. If we go to analysis, this is where we have all of our modeling over here on the left. All the rheology models. Or we can just right click on a data point and hit analyze, and we got the same stuff here. So this Canon S600 fluid is a Newtonian fluid. So I'm going to do a Newtonian model. And the viscosity 1.083, and it should be 1074 within 3%. So I suck at math, but I'm pretty sure that's within 3%. Okay, so we can also run an oscillation test on this. I need to do that. So if we go down here, flow, we do oscillation, we do a frequency sweep. We don't need to wait for temperature, we don't need a soak time. So I'm going to run a displacement. 1 to 10 hertz. And then how much data? Points per decade. And points per decade. Okay, so with a flow test, you're getting an actual viscosity, right? It's just like a viscometer. It's turning and it's giving you a viscosity. When you're doing an oscillation, we're looking for complex viscosity, right? So it's just doing its calculations and giving you a number. So if we right click, I don't want to look at storage modulus or loss modulus on this. We right click in the graph, I can select different variables. So I changed from radians to hertz, so I'm going to go, frequency. And then I don't need G prime, G double prime, so I'm going to clear those, but I want complex viscosity. And I am going to get rid of that complex viscosity and add phasing. So you can change any of those variables you want. This is giving us actual data point display, so it's giving us the torque and the displacement. And because it's a Newtonian fluid, it should be 90 degrees apart, right? If we were running a piece of steel, what would it be? Torque and displacement would be right on top of each other, right? Because there is none. Mm-hmm. So, and then all samples between are what's in between the Newtonian fluid and steel. Okay, so it went to idle. So now if we right click on a data point, I'm just going to stamp, annotate the curve with statistics and the mean of 1.085. So typically I find the complex viscosities are usually a little higher, but it's always within the 3%, right? So you do an oscillation if you wanted to do like some oil or fluid, something at a really high shear rate, because I've had people ask me, it's like, well, yeah, if you do that, oil's going to be all over the wall, you know? So just do like a frequency, at high frequency. Okay?
So how do we export the data?
How do you what?
Export the data, like get the raw data of.
Oh, you get raw data. Yeah, I should have showed you guys that. I'm going to run another test too. So, but if we go down here to these little tabs, you've got the experiment tab. So this is all part of the file, right? So you've got the experiment you ran, and then if we go here, we've got the raw data. And then here is the graph. This is the actual file. If we right click, you can export to Excel, whatever you want to do, or you can go up here and export. Okay? If we go to format, we actually have a report function in this software. Okay? And it's pretty simple, but it's easy. And it's pretty nice. So we could generate a report, right? It's anything that's over here, you can grab and drop. Not that. We want this, right? So anything you just. So it's kind of nice. It's simple. You can put an image in. You can do all your header footer stuff. And then that's saved as part of the file too. Okay?
Great.
Okay, so now we need to clean this off, and we'll throw in the other accessory.